Alright everybody, welcome to lesson 2 in our statistics unit. Today we're going to talk about the normal distribution, typically what people call the bell curve. And you see it used a lot in, post-secondary grading, especially with those super large classes of 400-500 people. Typically you hear that being said as, well, we're graded on a curve. And this lesson will help to explain, kind of what those features mean, what to look for, really what that whole statement means, right? What does it mean to be graded on a curve, and what does that mean for you? So when we've got a sample of data, when it's gathered and displayed as a histogram, with regards to frequencies and things like that, there are patterns, right? And the more data we have as that sample size increases, well, there's more bars. If you think about what a histogram is, really it's just a graph that's just got frequencies and data attached to it. Now, the more data I get, the smaller those bars happen to be. More often than not, if I have a lot of data, it'll congregate around a central point, right? It'll congregate around its average, right? And everything will end up getting spread out from that average point. And the more data you have, eventually it'll start to look like a flattened out kind of curve. If you compare this to the first scenario here, it's a lot of boxes. It doesn't really look like that curve fits. And I can kind of trace one, and I'll drag it around to show you what I mean here. Oops. Okay. So if I just drag this curve around here, you can see that it kind of fits all of this data, but when we get to places that have a smaller sample size, there's less data to use, it's not as precise to use a curve like that, right? It's when I get more data involved, that curve tends to fit a lot better. Okay, so I need a lot of data for this to work. Many data values. Now, these normal curves can be various shapes and sizes. This is not the be-all, end-all of these types of curves, and they can be skewed, left or right. And, they take various shapes. Like, this is just the perfect, ideal, normal distribution shape. And, it kind of looks like a bell, right? Which is why we call it that bell curve. Now, that curve will approach the x-axis, but it will never touch it or cross it. Okay, and the reason for that is the area underneath that curve represents a probability. So the total area underneath that curve must be equal to 1. Okay, the total probability of an event, right? If it's 1, it means there's a 100% chance of it happening. Now, I can't touch that curve because as soon as I do, that point will now say 0. And I can't really go under it because then I'm going to get into the negative y regions, which really doesn't make sense in terms of statistics here. Okay, so we're not going to touch that axis and we're not going to cross it, definitely. Now, in a normal curve, these three attributes are all going to be the same or very, very close to being the same. Right? If I rounded them, they would have the same value. So the mean, median, mode have to be equal in a normal curve, and if they are, well, they're going to be located at the center. Essentially what this is saying is if the mean, median, mode are equal in a normal curve, you'll find the average or the mean at the very center of it, right? The middle value, right? That's going to be our mean or our median, right? The middle point. The mode here, again, if you remember what mode means, it means the most repeated. And if this is a histogram that talks about frequency, the highest bar should be the one that repeated the most, which makes sense if you look at these curves. The highest bar is also in the middle. So those three features are all going to end up being the same in a normal curve where the mean is located in the middle. Okay, two numbers, the mean and the standard deviation, are going to characterize this curve. We already talked about the mean, where we would find it on that bell curve. We're going to find it right in the middle. But the standard deviation, if you remember from our last lesson, we talked about how far data values are spread out from the middle, right? From the mean. Now, if I have a larger standard deviation, all my values are going to be super spread out. But if my standard deviation is very small, all the values are going to be very, very close to the mean, right? And I could have a shape that if it's very, very close to the average, I could have a bell curve that looks something like this, right? Very, very vertical, right? Everything is really close together. Now, if my standard deviation is very high, I might have a bell curve that is looking really elongated and flat and spread out. Everything is just happens to be further away. So I get two different curves depending on what that standard deviation value happens to be. Okay, the mean gives us that central value or the symmetrical point. All of these curves are perfectly symmetrical down the middle, right? And the average is going to tell me where that happens to be. And again, the standard deviation is the spread, essentially, how far it is away from the average. Now, every curve is characterized basically by this picture down below. Now, we said they're symmetrical. There's a symbol here in the middle, right? Basically looks like a fancy U. That's going to tell us what our average happens to be. And we saw in the last video we had another symbol for the mean. It was the X with the bar on top. This is just another symbol for the mean. So it is always going to be in the center, right? That is our middle value. That is our mean. And I'll add that symbol down here too so we've got it. Now, the other symbol that you see here, it looks like an O with a little hat on it. That was our symbol for standard deviation. So essentially what this is saying is if I start at my average in the middle and I add one standard deviation to it, I get to the next data value out to the right. But if I subtract that same standard deviation, well, I get to a new data value on the left. So within one standard deviation of the mean, and that could be in a positive direction or a negative, right? Within that one standard of deviation, 68% of all of the data will lie between one standard deviation. So it could be the average plus a deviation or the average minus a deviation, but 68% of all data will fall in that range. Now, if I do this a second time and I add maybe two standard deviations instead, we're just getting further and further away from the average as I increase my deviations. Now, the further I go, the more data I will encompass, right? Which makes sense. Like if I add two standard deviations this time, and maybe I'll color this one in blue, well, now I'm going to take care of all of the stuff in the middle, that original 68%, plus the other sections off on the left and right. So in blue, we are taking into account more data because we're covering more of that bell curve. Now, within that two standard deviations, you'll see the number here, 95% of all data will fall between two standard deviations. And if I do this one more time, within three standard deviations, you will find that 99.7% of all data will fit in that range. Sorry, I got a little bit of a tickle. So we could use that idea, right? That symmetry idea with our bell curve to solve some problems, to make estimations. We do this in statistics all the time. So it's a little bit of a trivial example where this person has been collecting some data about dogs and their weight over a 5-year period. Okay, the average weight of the dogs is 46.2 kilograms, and the standard deviation is 1.6. So I'm asked here to think about what one value, or what is the value one standard deviation below the mean. Well, if I think about this, based on what we just talked about, I know what the average is, right? I know the average, and if I'm thinking a number below that average, that has to mean subtraction in math, right? Something smaller. And I'm going to subtract one standard deviation. So if I take my average of 46.2 kilograms and we subtract one standard deviation, I'm going to be able to find out what the value is that's one standard deviation below. So if we do 46.2 minus 1.6, well, now I know that that other value is going to be 44.6 kilograms. Right? And I can draw you a little bit of a curve here to talk about this. And I know what the average is, so I can put that number right in the middle, right? It's symmetrical. So here's 46.2. And one standard deviation below the mean means one value to the left of it, right? I'm below it. I'm getting smaller. So 44.6. Right? And I can determine the values above the mean as well. Above is just going to mean that I add this time. So I can take whatever my average is, and I'm going to add 3 standard deviations this time. So we'll do 46.2 kilograms, and we'll add to it 3 times 1.6 kilograms. Right? That'll give me the value I'm looking for. So 46.2 plus 3 multiplied by 1.6, since that is my value for one standard deviation, and I'm going to see it's 51. So here's one deviation, there's 2, here's 3. So way off on that right side, I'm going to have some dogs here that could potentially have a weight of 51 kilograms, or a mass of 51 kilograms if you're thinking in terms of physics. Okay, so these dogs are going to span a bunch of different values, and I don't really know how many dogs there are. I don't know how many that this person has collected data on. I know that it'll span a large number of values, but 3 standard deviations we said encompasses about 99% of all data. So I probably won't have any dogs with a mass greater than 51. It's not saying it's impossible, it's just highly unlikely with regards to, probability. So for C, it says this person, Stephanie, continues collecting data for another 3 years. And after analyzing this new data, the average weight of the dogs has increased to 48.3 kilograms. The value 2 standard deviations above the mean is 50.5. What is the new standard deviation? Well, now I've got to work backwards a little bit here. So I know the average this time, and I know the value 2 deviations above the average is 50.5. So now I got to do a little bit of working backwards here. So if I start with 50.5 kilograms, that should be equal to whatever the average was, 48.3 kilograms, plus 2 standard deviations. Right, and I can work backwards to find this number that I've actually added. So I'm really just solving a little equation here for that, of that unknown, that variable. So we'll do 50.5 minus 48.3. So I'll write that step in here too. So it's minus 48.3 on both sides. And it will leave us in a place that says, well, 2.2 is equal to 2 standard deviations. Well, I don't want 2 standard deviations, I only want 1. And this functions the same way as any other equation. I can divide both sides by that coefficient of 2, and I will now know that the new standard deviation is 1.1. Right? There's my new standard deviation, 1.1. So if I have specific data values, I can use them to calculate other specific data values. But if I have those values, really I can just talk about this in terms of percentages. Since I know, how symmetrical this is, I know how much data will lie in those ranges. If I'm told, for this example, just talks about trees, and from all that data collected, the heights of trees in a particular forest are normally distributed. So they are telling me that it should fit on a bell curve by saying the word normal and distributed. The mean height is 3.5 meters, right? So the average height of a tree is 3.5, and a standard deviation is 0.8. Let's label this curve with the average and the values for plus or minus 3 standard deviations. So really what this is saying is put the average on there and the values for 3 deviations above the mean and 3 below it. So our average, again, will always go in the middle. This is symmetrical, so there's my 3.5. And then I need the values that are above it. So 3.5 plus 0.8. 4.3 is the first value above that mean. Add it again. So add another 0.8 for my second deviation. That'll be 5.1. And one more time will get me all the way to a height of 5.9. Right, so roughly 6 meters. It's pretty tall for a tree. If I, go backwards to get the values underneath that mean, so 3.5 minus 0.8, we'll get 2.7. And we'll do it again, so minus another deviation. That'll take us to 1.9. And take us one more, way down to 1.1. So essentially, I could have really, really short trees, just over a meter, or I could have really, really tall trees right under 6 meters, right? And I could have every type of tree in between, right? So these gives me those specific values that are on those standard deviation markers. Now, that's part A. Part B, C, D, and E really get me to use those percentages to think about this. Okay, so for B, it says what percentage of trees is between the heights of 2.7 meters and 4.3 meters? Well, on my curve, this is the region we're talking about that I've shaded in red, right? The number of trees, the percentage of trees between these two heights. Well, I've just shaded in the region that is one deviation above the mean and one deviation below it. And since this is symmetrical, we said within that first standard deviation boundaries, 68% of all data will fall in that range. Every time something is normally distributed, it'll fall in the range of 68% within one standard deviation. Okay, so there it is for B. No real work to do. For C, what percentage of trees is between the heights of 1.9 and 5.1? Well, now I've got a new boundary to think about. Here's 1.9, there's 5.1, and I still have the red part in the middle. So now I'm within 2 standard deviations of the mean, right? And we said that accounted for 95% of all data. Right? So I know that if I have trees between a height of 1.9 meters and 5.1 meters, that should account for 95% of trees in this forest. Okay, the really, really tall trees and really, really small trees make up a very small percentage of this forest. Everything else accounts for the rest of the data. For D, we're asked what percentage of trees have a height less than 1.9. Well, think about this for just a second. I've just accounted for 95% of the data. So in total, there should only be 5% left. So from 1.9 and smaller than, or 5.1 and greater than, both of these regions in pink combined account for 5%, right? They have to, because I have 100% to use in total. Now, if I've got 5% to use in total, but I only care about what percentage of trees have a height less than 1.9, I don't care about the side that's 5.1 or more. So if it's 5% with those two combined, and this is a symmetric graph, right? The bell curve is symmetrical. Well, I know that the part that's less than 1.9 must be 2.5%, right? The 5% just gets split into two parts. So 2.5% is the little section that's less than 1.9. 5.1 and greater, that's also 2.5%. I just wasn't asked about that piece. Okay. Now, part E is us actually getting a specific number of trees here. Now, if there's approximately 250 trees in this forest, how many trees are expected to have a height of 5.1 or more? Well, I know the percentage of trees, right? I know that 2.5% of trees in this forest should fall in that range of height. I know how many total trees I have. So really what I'm looking for is 2.5% of 250, right? So really this is just a multiplication question because if I turn the 2.5% into a decimal, divide it by 100, we're going to do 0.025 multiplied by 250. And I'm going to get 6.25 trees. I can't really have a quarter of a tree. So if I'm looking for a number of trees I expect to have this height, I can't count that quarter of a tree. So I'm going to round down here. And really, I expect 6 trees to have a height of 5.1 or more. All right, I can't round up. I'll have too many trees. I know for sure I'll expect to have 6. I just can't count that extra quarter of a tree. Okay, so we can see how the percentages help us determine an approximate value, right? It's really helpful to give us an estimate, because if it's a forest, I can't go count all the trees and measure all of them, but I could, get an average and make my best guess, right? Where statistics really comes in handy. Okay, so if we actually have to draw out one of these curves, again, these curves are characterized by 2 numbers only, a mean and a standard deviation. That's really all I need to know to draw this. So a group of friends are flying out together on vacation. You've got men's luggage, you've got women's luggage, and you've got the average mass of both and the standard deviations of both. So all we're asked to do is, sketch a graph to show the distribution of masses of the luggage. So it doesn't really matter which one we do first, so I'll go in order here. We'll do the women's luggage first, and we'll color code it. So I'll use blue. Let's use blue. So I've got an average of 6.35. That'll go in the middle, right? 6.35. That's our mean. Standard deviation is 0.59. So 6.35 plus 0.59. 6.94 is one value above the mean. We'll do this again. 7.53. And I'll do one more. 8.12. Okay, and we'll go the other way as well. This just helps to give us, some points to use. If you can hear a child screaming in the background, it's just my daughter playing upstairs. 0.59. There's 5.76 and minus 0.59 again. 5.17. And one more time, 458. Okay. Okay, so there I've got 3 values above the mean, 3 values below it. So this gives me my value. So really, I'm just going to sketch this curve as best I can. Like, most values fall in that middle part. So here we go. Just gives us a nice bell curve shape. Okay, and then on this same kind of grid that we've got on the bottom, this same sort of, axis line, we're going to do the other values on here as well and see if that skews anything a little bit, because I've got a different standard deviation now. So if you think about this, since that standard deviation is larger, my numbers should be more spread out, which means my curve should look a little bit more spread out as well. Okay, so let me actually color code this. So I'll highlight the women part in blue, since I used blue to draw it. And we'll do the males in red. Okay. So the average is still the same. It's just the deviations that are different. So 6.35 plus 1.04. So my first one is 7.39. So somewhere in the middle here, 739. And do it again. 1.04. 843. So you can see I'm already past the values I had previously. There's 947, somewhere way out here. And again, just an estimate, doesn't need to be perfect. And we'll do the minus sides of things. Well, I guess, did I write that other one down? I didn't. Oh, I did. Yeah, it'll take a second. The iPad will just kick in here. So let's do the other part. 531. Now I'll add that one. About there. 5.31. There it is. And we'll subtract again, 1.04, 427. Okay, somewhere here. And one more time, 323. So really, so much farther out than the original. Now, this is just going to mean when I go to draw this graph, when I go to draw this curve, it's just going to be a lot flatter and more spread out. That's all it means. Okay, so it's going to look like it's way more spread out. Basically just a lot flatter, squished, stretched out, because all of those values for those standard deviations are a lot spread apart. A lot more spread apart because that deviation was larger. Okay, so I've got my two curves. That's what they're going to look like. Now, part B says that the women went shopping. Now, I've been on vacation before, and I do a lot of shopping too. So don't take this, too seriously. It just is something to illustrate the point that the average weight of the women's luggage increased by 1.2 kilograms. Right, the average went up. Now, sketch a graph that shows how the distribution of the masses of their carry-on luggage changed for the flight home. Now, it doesn't say that the standard deviations changed, right? It just says that the average increased. So I can recalculate all of those using the same standard deviation, but we are only asked to draw the one. So if the average increased by 1.2, well, now I've got a new average of 755. Okay, so 7.55 should be my new number in the middle. And, if I do my standard deviation from before, I believe it was 0.59. 814 is what I'm going to have. And another one for 873. And we'll do one more for 942. And we'll go the other way as well. So 755 minus 0.59. 696. And again, 637. And one more. 3 on either side, so 578. There we go. And I mean, the graphs don't look any different, right? It really is just, I can't even draw it now. Take my time here, there we go. It just has to be that bell shape, right? It is a normal distribution, so as long as you don't touch your axis, the only thing that will change is your numbers. The shape is relatively the same because, well, the average is the only thing that changed. The deviation was still the same, so the shape of that curve should still be the same. Right? It's only when the deviation changes where you see a different shape of that bell curve. Now we've got one last one to talk about here, which really is going to get us to use our calculator one more time, like we did in the last video here. So this is a good review place. And it says that Reggie recorded the points he scored playing basketball during the year, right? So these are all the different games that Reggie played and the scores he got in them, right? All the points he scored. Part A says determine the mean and the median of the scores round to the nearest tenth. So there's a lot of scores here. I don't really want to add them all up by hand and do that calculation. Maybe I miss a number, maybe I get something wrong. So we're going to go use our calculator to do that again. So we'll hit Stat, Edit. We'll be allowed to enter all these numbers into that list. So we got to put them all in there. So give me a minute as we put them in. So it doesn't really matter which order you put them in. You don't have to sort them, nothing. So I'll go 22, 24. I'll go across. So I think I got them all. 1, 2, 3, 4, 5, 6, 7, 8 by 3. There should be 24 values in here, and we'll be able to figure out if we missed one or not. So let's go calculate some one variable statistics here. So hit stat, and we'll go back to calculate, hit the right arrow key. One variable stats is what we'll do. Now I don't really have to tell my calculator it's list 1 because it's the only list present, but you can define it. Hit enter. So here we've got all of our stats. So N is 24. N stands for the number of data entries. So I knew there was 24 numbers. I have 24 there. We're good. I didn't miss one. Determine the mean and the median. Well, the mean is my X bar. That is our average. And it says to the nearest tenth, so 18.5. Okay, so the average number of points he scored in a game was 18.5. Obviously, some games were higher. He got 36 in some games. Right, he got 0 in others. So, the average in the middle. And the median, if I scroll down again, median is 21.5. And it straight up tells me it's already rounded to the nearest tenth. It's great. Now, are Reggie's basketball scores normally distributed, and explain? And we said at the very beginning of this that if a set of data was to be normally distributed around a bell curve, 3 values have to be the same: the median, the mean, and the mode. So his average is 18.5, the middle value is 21.5, and the mode looks like it's 0, right? 0 happens to be the most repeated value. So his scores would not be normally distributed since the mean, median, and mode are very different. So no, the mean, median, and mode are different. Right? And that normal curve is essentially a histogram. It talks about frequency. So the numbers that are in the middle have to be the ones that repeat the most. They have to be the ones that are in the middle. They have to be the ones that are the average. So all 3 have to be the same. Since they're different, this is not a normal distribution. Okay, so there is our lesson on the normal distribution. In the next one, we'll talk about the standard normal distribution, how I can take any data set and represent it a standard, consistent way, across examples. So underneath you'll find, a summary of everything we just talked about, a really helpful place to come back to, and some practice problems if you want to try them, along with the answer key to everything. So look forward to seeing you in the next one. Until then, take care.